Okay. Now let us take this, partial implementation that we did just for load word, and we'll augment it to add a few more instructions, right? Now I'm going to look at the store word. What is the store word? The store word is basically going to take a register value, right? It is going to do some operation on it, right? And it is going to do some arithmetic operation on it, get an address, and the other register S2 or source register 2, right? RS2 is going to be written to the memory. Okay, so that's the main thing here. So as usual, you look at it. What has happened is when the program counter has now become 1004, right? On the next clock edge, right? So if you look at this, in this clock cycle, my load word, what is that instruction that had? Load word x6 comma minus 4 of x9 was executed. Okay, now in the next clock cycle, we are going to implement the store word. Okay, so here what will happen? My PC next will just become 0x1008. This is my store word. Okay, and what is the instruction we are talking about? X6 8 x6 8 of x9. Okay, so what we are saying is take x9, okay, rs1, add 8 to it, treat that as an address, take the contents of x6 and write it to the data memory. Okay, so that is what is happening here, right? And with some delay, you will see that this becomes 0x1004. Okay, so that's what you see here. It has become 0x1004, and what you see here is basically the 0x1008. So effectively what you see, the values that you see here written in blue, right, are maybe sampled very close to the next clock edge. So data has gone through all the combinational blocks, everything has settled, and then you know what the final value is. Okay, that's what you see. So you sample at this instant, you will see these values. Likewise, earlier we would have done the sampling somewhere at this instant, right? So that's what you see, 1004, PC plus 4 has evaluated and that's become 1008, right? That's what you see here. Okay, and now what you're going to do, you're going to go through a very similar path, right? Except that now you need to treat RS1, okay, as the source register 1, okay, which happens to be again bits 19 to 15, the value is x9, so that is 9. Okay, now you will get that data, okay, which is going to be treated as some you're going to add it with that immediate data and get the address that you want to write into. Okay, the difference now is how the immediate data is actually treated. Okay, so let's look at this. So here this, we don't have the RD register, okay, because this is a store word type of instruction. That means you are only operating on source 1 register, source 2 register. There is no write back into another register here. Okay, so the RD field, remember the RD field always would have gone to this, would have gone to this A3. Okay, that's the important point, right? So here that A3 is not used. What you need to do is to treat that as immediate data 0 to 4, right? So that's what you are doing here, and you are basically going to take this opcode, get that immediate data, which is a combination of IMM 11 to 5 and IMM 4 to 0, and give it to the sign extender. You get the extended data. So you take this, right, this is 8, 1 bit from here and 3 bits from here, you will get 0 and 0, right. So that's why you get this 0x008, and then you sign extend, you will get all zeros there. You are going to now give this to source A, source B, make the ALU operate on this result, get you the address. Now what are you going to do with this address? You are going to write data into the memory, into the data memory. Okay. So what is the right data? What is the data that needs to be written in? It needs to be the data that is obtained from RS2 register, right, corresponding to RS2 register. Therefore, bits 24 to 20 which correspond to the RS2 register, right, are going to come here. That's what you see here, bits. That's why this is 6. That 6 here, right, is given to A2. On read 2 port, RD2 port, you will get the data that is sitting in that register. That is your write data into the write memory. And of course, for data to be written into the data memory, my clock has to pulse, my write enable has to pulse. Okay, so therefore if you look at it, I have some control signals that I am now adding in blue, write, IMM source and all that stuff, right. So we'll come to these control signals a little later, so that we can decide, we'll understand this when we implement the control path, right. So now there is no read data if you look at it, right. So all you have to do is, in order, so if you look at this signal here, the read data is just connected back to WD3 of the register file, but will data get written into that register now? For example, if you look at it, the A3, right, is getting bits which are this 11 to 7, right, that is what is here, right, and that is getting some data 8, that's, but does it mean that that is going to write into register X8? Answer is no. Why? Because this reg write signal has to be 0 for this particular instruction. So that's why it is important to understand that data can be written into a register not just by providing the address and the data. The clock has to pulse and your write enable has to pulse. Therefore, there is no problem in this data signal coming back like this to this WD3, because the reg write signal is not going to pulse here at this point. Okay. So with that, we have basically completed we have been able to add the store word instruction, right. So next let us look at one other important thing. So here if you look at this I type instruction versus S type instruction, the source bits are going to come from a very different point. You remember earlier we had discussed this, I type and S type, its only differentiator is the immediate encoding, and therefore that needs to be taken care of in the implementation. Okay, so we'll come to this a little later. Now I am going to go ahead, instead of immediate data that I am going to operate on, in both load word and store word we operated on some immediate data. Now I am going to say forget the immediate data, I am going to operate only on registers. Okay, that means there is no data memory access in this case. Okay, data is in the registers, you are operating on something and then you are coming back and writing data into a third register. So you have RS1, RS2 and RD. Okay, so here for example the instruction we are looking at is in 1008. Okay, so 1008 is where the OR is sitting. Okay, and basically we have got that PC here, PC plus 4 is 100C, right. At 1008 you are going and fetching 32 bits of information. It tells you from this 7 bits that it's an OR type of instruction, right. And therefore now what do I need to do? I am going to decode this machine code exactly the same way that we did for the other two instructions. So bits 19 to 15 is going to give me RS1, bits 24 to 20 is going to give me RS2, right, RS1, RS2, and bits 11 to 7 is going to give me the destination register here, okay. So that's why you see here that in this case we are doing OR of X5 and X6 and putting it into X4, right. Therefore, the A1 is 5, RS1, A2 is 6, right, and A3 happens to be, destination is 4, register X4, right. So what you are doing here, you are giving these two addresses, you are going to get the data on RD1, RD2, right. You will get some data out here, it says the contents of that register happens to be 6 and 10, okay. So we will not worry about that right now. So it is sitting there with some particular data. Now what you see is the source A for the ALU. The ALU is operating on 2 operands always, mostly for most instructions, right. Source A is always this the register data RD1 corresponding to RS1 of the instruction, okay. That's why it is important to figure out this decoding accurately, right. You got source A there, right. Now source B on the other hand could be one of 2 things. In the last 2 instructions that we saw, load word and store word, it was the immediate data, okay. On the other hand, now it is the register data corresponding to RS2 and therefore it is this RD2. Therefore, you need a multiplexer here in order to choose between these two, and you need another control signal called ALU source, right. And you are now going to do some whatever with it, and if you look at this, your ALU control, there is another control which is going to tell you, okay, do the OR operation on this, right, and you are going to get the ALU result here, okay. So let's look at the implementation here. So what has happened now is you have got the ALU result, okay. So you have done OR of 6 and 10, okay. 6 and 10 you have done, or when you do, you will get the result as 14, okay, effectively, right. So what are we talking about? We are talking of 0x0110, which is 6, not x, sorry, binary, right, and we are talking of 10, 1100. So when you OR this, what will you get? You will get 1110 bitwise OR, and that's why you get the result as 14. This 14 corresponds to this, okay. That's the ALU result. Now what do I need to do? I need to write this data back into my register, okay. Earlier the implementation that we had, this read data from the memory was coming back into this WD3 port blindly. There was only one path, but now I cannot do that because in this instruction there is no memory operation at all. It's a purely register operation, and therefore we are bypassing this. What was the address in the previous 2 instructions is actually now the answer, and therefore we are bypassing that and giving it to a mux. And we have another control signal which is going to choose the result source to tell us whether you have to choose you're going to choose between the register and the immediate data, right, or the immediate data based data obtained from the data memory. So this you're going to choose between read data here and the register result, ALU result that you just calculated, and that answer now comes back and will come back to this WD3 for writing back. So the 14 answer has now bypassed all this path and is ready. Now what determines whether you write into this register or not? Again, it's this reg write signal. This goes high, okay. Note that in this case my mem write has to be 0, otherwise you will end up writing into that memory. Okay, whatever data came from the ALU is fed to that address port of that memory, right? But I don't want to write, and therefore my mem write has to be 0 in this case. Likewise, my reg write has to be 1. Okay, the corresponding reg write has to be 1 because I am writing back to the register out here, right? And effectively on the next clock edge, right? Remember, on the next clock edge, remember the write is sequential and will happen only on the next clock edge, right? It will happen just after the next, as soon as the clock pulses, the write will actually take place, right? That is what is going to happen here as well. Okay. So now what you do is, we are now going to take, we have implemented load word, store word, register operation, right? Now, by the way, we implemented register operation for OR. Now, what do you do if you want to do AND, add, subtract and all? Well, it's very simple. None of these things change. Only that arithmetic operation that you choose in that function 7 to 0 will basically change, right? In some sense, we are going to choose the combination of F3 and F7 is what is going to tell us what you want to do with that, what ALU operation you want to perform. Okay. Anyway, so now what are we going to do? We are going to look at the implementation of branch on equal. Now, what is the branch on equal? You have again two registers, okay, BEQ X4, X4, comma L7, right? So effectively, what we are saying here, right, is this is two source registers because there is no destination register. Now, remember, all the operations that we did, okay, started with one flip-flop latching some data, which was the program counter, and data got written back into some other sequential element. It was either a register or a memory, data memory, right? Now what we are going to do here is, we are going to implement a branch type instruction where you want to compare two registers, branch on equal. That is, you want to cause the program counter to take that branch if the two register values are equal, okay? And so you are saying, therefore, RS1, RS2 has to be this, two fields, right? That is going to be compared. The register values are going to be compared, by the way. And then you are going to implement a branch. What is the branching operation? It means that the PC target should be the current PC plus some immediate data. Okay, you are going to, you can do a relative branch. From the current PC, you add some address and then go to that new location. So what you are doing here now, you are basically getting in 0x, 100C, you have this branch on equal instruction, which is this nice opcode here, and that has been fetched from your instruction memory FE420A-E3. Okay. Now what are you going to do? You are going to decode this. I am going to deal with two source registers. Therefore, fields 19 to 15, 24 to 20 are going to be decoded in the inputs to the register file A1 and A2. You will get the data on RD1 and RD2. Here in both cases, we have given X4, X4. Of course, the two registers values will be equal, whatever the value in thing. So this BEQ X4, X4, L7 is the equivalent of a jump that we saw in x86. That is an unconditional jump, because of course these two register values will be equal, right? So you have obtained this 14, 14 here, right? And I am now setting my ALU source to 0 because I want the register value to go through to the ALU. The immediate source also has to be set appropriately because I am going to now treat this, as immediate data, right? And then you are going to do sign extension, get that data here, okay? So remember what we are doing. We want the immediate data to be added to the PC and the new address to be determined accordingly. So therefore what we are doing here is you're going to use this ALU to perform a compare operation, right? Or you do a subtract operation, right? Subtract operation, and there is a flag called 0. Just like the 0, we had a carry flag, 0 flag and all that in exercise 6. In the RISC V, we have only a 0 flag. So the 0 flag is after the result, after the ALU operation, if the answer is 0, the 0 flag will go high, right? So you are going to use this 0 flag, which will obviously be 1, right, in order to calculate this new target address. So you are going to take the PC value from here, give it to another adder. Remember, this is not the same as the ALU. This is a different instance of an adder because the ALU needs to perform the subtraction operation between the two source registers RS1 and RS2 that you give, okay, and therefore the ALU is needed for that ALU operation. The PC target is now going to just simply be an addition of this sign extended number. You don't need complicated arithmetic there, okay. So therefore that is just a thing. You give it here and then you get this answer back into PC target. And now what you do here is you are going to determine the PC source. This is the control signal, remember. The PC source is going to be a control signal to the mux, okay, and that is going to choose between two things. One, normally I would be adding 4 to get the next program counter value, right? But in this case, I am going to do some complicated branching operation, and therefore these two are, I have to choose between these two, and that's why that mux is needed for my PC next appropriately, right? So with that, what we have been able to do is to cover the basic implementation of these 4 operations that we had discussed, okay. So again, what is highlighted here is basically how the I type, S type and branch type instructions, the immediate data is going to be decoded, right? So what is going to happen is, we have this immediate source, IMM source 10, that is going into this sign extender, okay. So what it will do is, this sign extender data, it will take bits all the way from 31 to 7. See, the OP bits are 0 to 6. So this is 0, this is 6. So starting from here, 7 to 31 goes into my sign extender. Now, it doesn't mean that the sign extender is going to treat all these 25 bits as immediate data. What it does is, it chooses based on this IMM SRC 2 bits. If it is 0, 0, that means you treat instruction 31 to 20, right? I type instruction 12 bits and then sign extend bit 31 to 20 times, and you will get the 32-bit immediate data. On the other hand, if it is 0, 1, which basically is the S type, then you are going to take instruction 11 to 7, 31 to 25, and then 31 will be extended for 20 bits. 10 is when B type instruction, right? So that is going to be again some very complicated decoding of this immediate data from the instruction, right? So inside this extender is basically just a bunch of multiplexers and sign extenders that are used to implement this whole thing. So what is IMM SRC? It's basically a control signal that we have not yet shown you how to get it, okay. That needs to be done as yet at this point, okay.